Okay, folks, we are finally in the home stretch here after a very long, very detailed quadratic section. We just have a few loose ends to tie up. First thing we have to talk about are quadratic word problems. These are very similar to what we saw when we talked about modeling questions, quadratic modeling questions back when we discussed vertex form, I believe. In quadratic word problems, what's going to happen is we're going to get some real life scenario or data that can be modeled with a quadratic function, either a quadratic function that we have to create or a quadratic function that is given in the question. And what we are going to need to do is either figure out what the parts of the quadratic function or model are doing, or we might have to throw some numbers in certain parts of the model in order to find the values of other parts of the model. Example 36 is a reasonably straightforward example that will illustrate what I'm talking about. If you want to try this one on your own, pause the video and do so. So in example 36, we have Derek hitting a ball across a flat level field. The path of the ball can be modeled by the equation above. So we have this equation. It's clearly a quadratic because of that square right there. And we should be able to tell that this quadratic is in vertex form. This is a vertex form quadratic. Where was I? The path of the ball can be modeled by the equation above, where x represents the ball's horizontal distance in meters from the point where it leaves the bat, and h represents the height of the ball. So there's the height of the ball, there's the horizontal distance of the ball in meters above the field. The ball reaches a maximum height of 16 meters above the field after it has traveled a horizontal distance of 30 meters after leaving the bat, and the height of the ball at the point it leaves the bat is 1 meter above the field. Determine the following. So we need to know what the A, the D, and the P are. The A, the D, and the P. So what we're first going to do here is we're just going to, I'm going to circle that. We're just going to sort of look at what's going on here. So first of all, we know it's a quadratic, so we know we've got a parabola. We know, number one, because of sort of common sense and background knowledge, that a ball is normally going to look something like this. I should say the path that the ball is going to take is going to look something like that. Now you might say, well, you know, how do we know the ball's not going down and then up? Well, again, number one, because that would defy gravity, kind of. And number two, because they tell us that the ball leaves the bat at 1 meter above the field. So this right here is basically the point 0, 1. That is our y-intercept right there, right? If x is the ball's horizontal distance from the point where it leaves the bat, and h, the vertical axis here, is the height above the ground, well, when the ball is basically leaving the bat, at the point that it's leaving the bat, our horizontal distance is going to be 0, right? If we're on the bat, then we are 0 meters from the bat. We have not left the bat. And this says when we leave the bat, at the point we leave the bat, we're 1 meter above the field. So again, we start at 0, 1, and then we are also told that the ball reaches a maximum height of 16 meters after it has traveled a horizontal distance of 30 meters. Well, remember, horizontal distances, that's an x value, and vertical distances, that's an h value. So this point right here, the maximum point, the maximum height is going to be 30 meters, 16 meters, right? This is the horizontal distance, and this is the height. So when the ball is 30 meters past where it left the bat, 30 meters horizontally from where it left the bat, that ball is also 16 meters above the ground. Well, folks, that is our vertex. And now that's pretty much all we need to get what D and P are going to be, because remember, in vertex form, D is the x coordinate. Remember, D is like the h, right? If I write down y equals ax minus h squared plus k, well, whatever is in that h position, in this case that D position, we are going to have the x coordinate at the vertex, and whatever is in this k or p position, p in this case, k in vertex form, that's going to be the y coordinate at the vertex. So I now know that my equation up there is h equals ax minus 30 squared plus 16. So I now at least know that d is going to be 30 here and p is going to be 16. Now in terms of finding a, the way that we do that, and we did talk about this earlier in this section, we said that if we pretty much have everything except that a value, what we would need is we would need a number that could go in for h and x. In other words, we would need another coordinate, another pair of x and y values, remember h is like our y here, that we could throw into this equation so that we would be left with only one unknown, the a, and we have that other point. We have that other point right here, 0, 1. So this is hopefully going to make it really easy. We take the 1, that is a height, that is an h value or a y value. We're going to throw that in over there for h. The a is still unknown. The x is 0, so that's 0 minus 30. I'm getting the 0 from right there. So again, I've just thrown in my 0 and my 1. And plus 16. So what am I going to do here? I'm going to, first I'm going to subtract the 16. Subtract the 16, I get negative 15 equals a times, I'm just going to do this all at once. This is negative 30 squared, and negative 30 squared is 900. So let me actually just write 900a. Again, negative 30 squared, negative 30, that's 0 minus 30. Squared is the same as 30 squared. How would you figure out 30 squared? Well, again, you could just know that it's 900, or you can do 3 times 3, which equals 9, or 3 squared equals 9, and then remember you got to add in 2 zeros. So 30 times 30, you can do again 3 times 3, and then add in the 2 zeros, we get 900. So now I have 900a equals negative 15. I'm going to divide by 900, divide by 900. How should I break down that negative 15 over 900? I will do it by, there's various ways I could do this, but probably the easiest way, I'm going to divide by 3. So I'm going to get, divide the numerator by 3, I get negative 5, and divide the denominator by 3, I get 300. And now I'll divide by 5. So this is going to be negative 1, and then 5 into 30 is, 5 into 300 is 60. 5 into 30 is 6. Therefore, into 300 is 60. So I now know that my a value is negative 1 over 60. Negative 1 over 60. So this complete equation is now h equals negative 1 over 60, parentheses, x minus 30 squared plus 16. And now that I have this complete equation, I can figure out what my height above the field is at any horizontal distance. So if I were told that my horizontal distance is, let's say, 10 meters, I could take that 10 value, plug that 10 value in for x, and I would be able to get my height. I could also find my x values if I were given a height. So if I knew the height was, I don't know, 14 meters above the field, I could find out what my x value, what my horizontal distance past the bat is. So that's how we do a question like number 36. We really just use our knowledge of vertex form, and we have to integrate the information that's being given in the question into what we know about a parabola and how that parabola relates to vertex form. Down at the bottom of the page, we're going to see another quadratic word problem, this one that involves a area of a polygon scenario. These are not uncommon on the test at all. Remember that when we find the area of polygons and circles, we are squaring a quantity, or we are that's in the case of a square, or in the case of a radius of a circle. Remember, to find the area, we square the radius. To find the area of a square, we do the side squared. But even when we're finding the area of a polygon, let's just say a rectangle, remember that when we do length times width, well, both the length and the width are going to have the same units. For instance, we might have inches and inches. And when we multiply a quantity of inches by another quantity of inches, what do we end up with? We end up with inches squared. And remember, anytime we're dealing with squares, we are really talking about some sort of a quadratic function, some sort of a quadratic relationship. So if you want to try number 30 on your own, go to it. We can use a calculator on this question. So if you need to use a calculator, certainly feel free to do so. In number 30, we have a rectangular poster has an area of 560 square inches. There's those square inches that we were talking about. The length x in inches of the poster is 8 inches longer than the width of the poster. Which of the following equations can be solved to determine the length? So determine length, I think that's all we need to circle. So we just need to determine the length, and maybe I'll circle this. Following equations determines the length. Great. So let's take a look at this. They tell us that x is the length. I'm going to jot that down. They also tell us that the area is 560 square inches. They also tell us, this is probably the key here, they say the length is 8 inches longer than the width. That means that the width equals the length, which is x, minus 8, right? The length is 8 inches longer than the width. So the other way we could write that is that the length, I should actually just translate this purely, the length x is 8 inches longer than the width. So that's width plus 8. All I have done here is I have just subtracted the 8 from both sides to isolate the width. Again, I just did that in one step, but you can see how it works from doing the translation in the question. This phrase here can be translated into this here, and then this equation here can be cleaned up to isolate for the width. So in order to integrate all this information, remember that the area of a rectangle, which is what we're dealing with here, rectangular poster, is going to be the length times the width. Well, now just substituting, we know that our length is x. That comes from right here. They told us that in the question. And the width itself is x minus 8. That comes from right here. I'm just substituting x minus 8 for the width. And we know that that product needs to equal 560. Well, all we got to do now is distribute. X times x is x squared. X times negative 8 is negative 8x, which equals 560. It looks like that equation right there could be solved. That is a quadratic equation that could be solved for x, and we would have the length of the poster. So x squared minus 8x equals 560 is what we need. X squared minus 8, x squared minus 8x, that looks good. X squared plus and plus, no, and we are done. So, like I said, that's a fairly common example of a quadratic word problem or a quadratic modeling question that you will encounter on the test. At the top of the next page, we have a much more difficult version, an advanced quadratic word problem. This one, I will say, if you want to try it on your own, by all means, go ahead. I have a feeling that the vast majority of students are probably going to get a little stumped by this one. This is a tough question. So, example 37, the fuel economy of a vehicle in kilometers per gallon, kpg, can be modeled by a quadratic function of the vehicle's speed. Okay, so there's some function out there, function of the vehicle's speed, that will model the fuel economy of a vehicle, whatever. An engineer is testing a new vehicle's fuel economy and finds that the vehicle achieves, look at that language right there, maximum fuel economy of 48 kilometers per gallon at a speed of 82 kilometers per hour. In high speed tests, the engineer finds the fuel economy drops to 32 kpg at 122. All right, whatever. What is the vehicle's expected fuel economy? 92 kilometers per hour. All right, so let's see what's happening here. Maximum fuel economy of 48 kpg at a speed of 82. So what that means is there's going to be a parabola that looks like this because it has a maximum. So we know the parabola is going to look like this. If we were graphing this on an XY plane, it really wouldn't be an XY plane. It would be that fuel economy, which I guess I'll call F, would be on our y-axis, and speed would be, so S, would be on the x-axis, the horizontal axis. Why do I know that? Well, because they told me right here that this is a quadratic function of the vehicle's speed. When we say that the fuel economy is a function of the vehicle's speed, well, remember, when we write something like f of x, this means that f is a function of x. So in the same way down here, we have that f, which is the fuel economy, is a function of s, right? The function of the speed. So this is f of s. And remember, when we have f of f of x. Obviously, this thing here goes on the horizontal axis, so that's why I'm putting the s on the horizontal axis, because the s is like our x, and the fuel economy itself is like the y is the vertical axis. So this point right here, that point right there, they tell us in the question is 82. That's the speed. Okay, so that's the x value, and 48. All right, so this is kilometers per hour, and this is kilometers per gallon. That is the maximum point. They tell us that in the question. And now, folks, just like we did on the previous question, we can write this. Why can we write that? Well, because remember, this is the h position and this is the k position, and h and k are the coordinates of the vertex, in this case a maximum of our parabola. So I know that my function's sort of skeleton is what I just wrote. Now, in terms of finding this a, just like we did on a previous question, remember we need another point, and we have another point. We have another point right here. This point, 32, 122, is somewhere, I don't know, it's somewhere, let's say, over here. Okay, so maybe 122, and then this guy here is 32. It's some point past the maximum. And again, that's very simple to understand, or it should be simple to understand, because our maximum occurs at a speed of 82, and now we're at a speed of 122. So again, we've got another point somewhere over here. Does it matter where that point is? No, it just matters that this is another point on this parabola. And now what I can do is I can take that 32, which is a fuel economy, right? I can throw that in for my f, and I can take the speed, the 122, and I can throw that in for my s. And now I have everything in numeric form except for that a, which means I can now solve for my a. So I've got 32 equals 122 minus 82. I cannot use a calculator here, so I'm going to do that in my head. That's 40 squared. 40 squared, I'll do that in a moment. That's 40 squared times the a plus the 48. I'm going to subtract the 48, subtract the 48. Over here, I am going to get, what's 38? 32 minus 48, well, 48 minus 32 is 16, so this has got to be negative 16, and that is going to equal 40 squared is going to be 1600. That's 4 times 4, which is 16. Have to add in the 2 zeros, so that's 1600. Look at that. That's going to end up being quite nice. I then divide both sides by 1600 to isolate my a, and what do I get? I get a equals negative 1 over 100. 1600 divided by 16 is 100. I'm just doing the reciprocal of that, 1 over 100. So I now have my a value, which means I have a, I'm going to get rid of this over here, or at least I thought I was going to get rid of it quickly. Now I have my fully formed function. I have that f equals negative 1 over 100 times s minus 82 squared plus 48. And finally, the question itself is asking, what is going to be my f, my fuel economy, at a speed of 92 kilometers per hour? That's going to end up being quite nice, because when I put 92 in here, 92 minus 82 is just 10. So I've got f equals negative 1 over 100 times 10 squared, which is 100. Let me write that. Again, that's going to make it quite easy for me to do this calculation. Negative 1 over 100 times 100 is negative 1. The hundreds just cancel. So this is just negative 1 plus 48. And lo and behold, we have 47. So our fuel economy at 92 kilometers per hour is going to be 47. Again, is it going to be very common that you get a question like this? No, probably not. This would be something that you would see possibly once every 5 tests or something like that. Having said that, it is yet another good example of the kind of question that becomes not completely impossible if you know a little bit about vertex form and what it means to talk about the maximum of a function, and how that maximum of a function relates to the parabola, and how the parabola relates to the vertex form, and so on and so forth. So that is it for quadratic word problems. The last thing that we need to talk about is the fact that occasionally you are going to see a question that might sort of make you think of quadratics and make you think you have to know one of the 1,000 things that we learned in this section. And then if you actually just take a breath and examine the question a little bit more closely and with less anxiety, you might see that the question is actually not at all a true quadratics question. You might find that you just have to use some basic algebra or even arithmetic to solve the question. Example 38 is a good example. I would try this on your own. In example 38, in the xy plane, the point 2,5 lies on the graph of the function h. If h of x equals k squared minus x squared, where k is a positive constant, what is the value of k? So we need the value of k. So again, some students might look at this and immediately think, oh, that's a difference of squares. Maybe I should factor it. But you got to remember that when you see a point given, or an x and y coordinate, I should say, you know that indeed the 2 is an x value and the 5 is a y value, although a y value here is h of x. So that 2 is an x value, that 5 is an h of x value, which means, folks, this is not a quadratics question at all. This is a substitution question. This is a question in which we just have to take the 5 and plug it in for the h of x. We have to take the 2 and plug it in for the x. 2 squared is 4, so I'm just going to write down 4. And again, at this point, students might be thinking, I guess I've got to difference of squares this guy here, and that is not the case. All we have to do is add 4, and we get that k squared equals 9. And now we square root both sides. Remember, we've talked about this a few times in this section. We do have to account for both the positive and negative value. Fortunately, in this case, they tell us that k is a positive constant, which means we know that the 3 is the correct answer here for the value of k, which is what they are asking us for. So again, really not a whole heck of a lot of quadratics involved in this question. This just becomes a substitute and solve question, and the solving really is stuff that you learned when you were doing some basic algebra in school. On example 39, in the xy plane, again, this is one you might want to do on your own before you watch me do it. In the xy plane, the parabola with equation y equals whatever intersects the line with equation y equals 11 at 2 points x and y. What is the length of segment xy? So we need the length of segment xy. Okay, so y equals 11 and y equals blah, blah, blah. They intersect. Well, what that means is, yet again, we have a substitution opportunity here. What we can do is, if we know these two, so here, let me do this. So let's say there's this line y equals 11. Clearly, this is a parabola. Well, we know that these two things, this parabola and this line, they're going to intersect at 2 points, x and y. So we know that at this point, which is on the line y equals 11, that point on the parabola will have, it must have, a y coordinate of 11. And this point too on the line has a y coordinate of 11, and therefore on the parabola must have a y coordinate of 11, which means all we need to do here is find the x coordinate, which we can do by substituting 11 for y. So we get 11 equals x minus 6 squared plus 2. We subtract the 2, we get 9 equals x minus 6 squared. Again, no need to FOIL this out. You could FOIL it out. It's not invalid to do it that way, but we can square root both sides as long as we remember that this means, because we are squaring a variable expression here, we have to account for the fact that x minus 6 could equal 3, positive square root of 9, but it could also equal negative square root of 9, which is negative 3, right? If x minus 6 equals 3, 3 squared would equal 9. If x minus 6 equals negative 3 squared would also equal 9. So we have to account for both scenarios, which is how we are going to get the x coordinates at both of these points, x and y. So plus 6, we get x equals 9, plus 6, we get x equals 3. So one of these has to be a 3, one has to be a 9. Let's do what we need to do, which is 3 on the left, 9 on the right. They wanted the length of segment xy. Well, the length of a segment between 9 and 3 is 9 minus 3, which equals 6. The length of segment xy is 6 here. So again, are there quadratics involved? Obviously, there's a quadratic involved. It's a parabola. Does the fact that we're dealing with a quadratic here really matter to this question? No, not really. We just have to substitute the 11 and solve for our x value. Deep breath, everyone. That is it for quadratics. We have finally made it through this, I don't know, 3 or 4 hour section. Quadratics are important on the SAT, and therefore it is important that we be thorough and specific about the information that we will need. So that is all for quadratics.